Okay, let's get started. So I'm going to continue with linear algebra today, and actually I think I'll pretty much be done with linear algebra by the end of this week. So we'll start with signal systems and transforms next week. So today I'm going to focus, today and actually most of this week will be focusing on eigenvalues and eigenvectors. And the last class actually been stochastic matrices, but this lecture and next lecture will be on eigenvalues. How many of you have seen eigenvalues before? Could you raise your hand? Okay. All right, so pretty much everybody has seen it. So this would be sort of, I guess, revision for you. One thing that I find is that many people understand how to compute eigenvalues, but they don't necessarily have a good intuition for it. What does it mean, or why is it important? So let me re-ask that question. How many of you think you understand why eigenvalues are important? Or, I mean, really get it, you know, like if you look at a matrix, you can say, yeah, these must be the eigenvalues, and this is why it's important. How many of you? Okay. So, unfortunately, this is what happens when you do eigenvalues in undergrad class. You have the mechanics of it. You kind of, somebody can give it to you. You can go through the computation and come up with it. But you don't necessarily have any idea what it means or why it's important and why people make such a big deal out of it. So hopefully by the end of today's class, you should have a much better understanding of both how to compute eigenvalues and why they're important. And when you do control theory, you will see very clearly what happens with eigenvalues. Okay, but the first step is to understand what's meant by a linear transformation. Okay, and a linear transformation is essentially a way of taking a vector and transforming it into another vector. Okay, so we take some vector. Let me just write it out. I'm going to do the example from here. So let's say we just have a vector with two elements, it's A and B. Just keep it simple. And what's going to happen is that we're going to compute from this a new vector, which is 2a plus 3b and 6a plus 2b. So this is a vector, this is another vector, but what's happened is that in this vector, the first element has gotten a weighted sum of these two pieces. Okay, if you recall what when we talked about the linear dependency was, you see that this is just a linear dependency of 2a plus 3b is linearly dependent on a plus b. So if you think of a and b as being some basis or some set, 2a plus 3b is just a weighted sum, 2 times a plus 3 times b. So take 2 times the first one and 3 times the second one. If you want to make it more interesting, you know, just make these weights add up to 1. So you could have, you know, 0.2 and 0.8, for example. Then you're getting some kind of mixture of a and b. Okay, that becomes this element, and this element is again a mixture of these two. So if you go back to the example I had, you know, with the Mongolian grill, right? If you go to Mongolian grill, and you have over here, you know, some tofu and some spinach. You know, this gives you the menu, the recipe for making for the first customer. This is the recipe for the second customer. Okay, it's a linear combination of these two elements. So in some sense, what we're doing is that we're taking a representation of the basis of you know, which are the individual elements, and we're applying to it something which allows us to compute what this combination are. It turns out that this is it's just a matrix. This matrix over here, 2, 3, 6, 2, is the trick, if you will, or is the recipe that tells us how to go from here to here. So you can just put this as equal to now, because what we're doing is we're taking this matrix and applying it to this vector over here. So any matrix, any square matrix anyway, can be viewed as a transformation. Okay, and that is the secret to the whole thing. Okay, if you understand that, you'll understand sort of what eigenvalues and everything are all about. So what we're trying to do is we have some vector, and through some physical process, we know that it becomes some other vector. Okay, and the trick is that we're representing the transformation in the form of a matrix. Okay, once you do this, then you get this transformation right here. Okay, so so matrix multiplication becomes really a way of applying this transformation onto this vector over here. Now the interesting part is that the effect of this matrix on this vector, it doesn't really depend on this vector at all. It could be AB or CD or whatever. The matrix is what's important. Okay, as long as you can use this as an operator, as a transformation, you can apply it to anything that you want. And so the properties are related to this. This is where we focus our attention on. This just happens to be the vector that we're working with to get this transformation over here. Okay, we could put CD or any number over here, you would still get the same transformation. Okay, so what we're trying to do now is we started out with the matrix as being just this bunch of numbers. You know, you have a bunch of counts of TCP and UDP and things like that. And now we're kind of moving further along. We're actually attaching some semantics to the matrix. We're saying that this matrix is going to have this property of being viewed as a transformation. Okay. So are there any questions about this over here? Okay. So just to give you a sense of this, that's why I had those two homework questions. So the first homework question was saying, what was it saying? Okay. So how do you get from ABC to the vector, I think 3A plus 2B plus 9C, or something like that. So if you use this matrix, 3, 0, 0, 0, 2, 0, 0, 0, 9, sorry, it's not plus. 3A, 2B, 9C. We see that we get the effect that we want. Okay, and we need zeros here because the first one is being multiplied by a scalar value. The second is multiplied by a scalar value. Third one is multiplied by a scalar value, and in fact, all the others are not being. So this matrix here is scaling up each of these components by a scalar value, and there's no mixing at all, right? And so that's why this can be viewed as a transformation matrix. Think of some kind of balloon, and in x dimension it expands by 3, by y dimension expands by 2, and z dimension expands by 9. So that's what the scaling is doing. It's pushing it in different directions by different values. Okay, so this is the operator over here. So I hope most of you got this right. You must have exchanged your whatever your cards and so on. Okay, so any questions about that? So that's just to give you a sense of the transformation in the, and for the general case, we need to just have the AI over here, AK, and this will be AN, and that's going to give you the same effect. It'll be, or whatever. So that's going to give the, or maybe just I call it x1 to xn, and it gives you the same effect of the scaling from A1, x1, AN, xn. So that's the same kind of thing that's going on over here. And again, that's the solution to the second homework problem. So as you can see, what's happening is that we are now mentally kind of going on to choosing the matrix in a way so as to achieve a particular kind of output. Okay, we're choosing this to do the right kind of scaling. Okay, and that's again the mental process I wanted you to go through for this. Okay, any questions about that? Okay, so the next thing I want to talk about is this notion of composition, and I want to do an example of that composition. So we let's just say that we have some matrix A applied to vector x gives you some vector x prime, okay, and some vector b applied to x prime gives you the vector x double prime, okay, and so we recognize A and B as being transformations. So the question is, what do we have to do to go from x to x double prime, okay? And I mentioned to you in the first class about the, or maybe second class, about the notion of multiplication. Why do we choose multiplication? And the reason is because the way we go from x to x double prime is that we are applying b to ax, okay? And so if you're going to apply, if you say this is given by the matrix C, then we find that C equals BA. And of course, in that order, it's not AB, but it's BA. So what we're doing is that the matrix product of two transformations results in a matrix, okay, which gives us the effect of those two transformations. So we now have the ability to think of what we can think of as algebra for transformations. Yeah. Okay. So people are coming in late. Okay. Look, you're disrupting everybody, disrupting me, most importantly. Okay? Don't do it. Okay? You can leave a few minutes early and get here on time. If I can get here on time and everybody else can get here on time, so can you. Okay? So from now on, all of you coming in late, just don't do it. The class starts on time. I said that in the first class, which you missed. Okay? So don't do it. It distracts me. It puts me off my schedule. And it's not good. Okay. All right. So the whole purpose of defining matrix multiplication in the way that we defined it, which is not the obvious way, because addition was the obvious way. We just add row by row, element by element. But for multiplication, we did something funny. And that's because of the fact that when you define it that way, we get a very nice algebra for transformations. You can take any transformation, any other transformation, and you get this product, and that gives us the combined transformation. To show this, let's just try it out. So we've already seen this over here. We've seen that this matrix over here, 2, 3, 6, 2, is going to give us this transformation of 2a plus 3b, 6a plus 2b. Okay? Now let's take this matrix, or this vector, I'm sorry, 2a plus 3b, 6a plus 2b, and I'm going to apply to it the transformation, which is a very simple transformation, 2, 0, 0, 2. And from your homework, you'll realize that what this is going to do is to multiply each element by 2. It's a scaling by 2 in both dimensions. So this is going to give us, just by inspection, 4a plus 6b, 12a plus 4b. Right? That's just because that's the scaling. That's the that's the homework assignment. How do you do the so that's a diagonal with the a1 equals a11 equals 2 and a22 equals 2. So that gives us what we want. So the question is, can we get this final result over here more easily? And the answer is yes, because we can use this rule, C equals BA. So what we're going to do is, I'll just use this over here. So I'm going to take this matrix 2, 0, 0, 2, and apply it to this one over here, because that's what I said. This is B, and this is A, and that should be equal to C. And this one is going to be 2, which is it? I can't read from here. So 2 times 0 is 4, sorry. It will be 4, 6, 12, 4. And if we apply 4, 6, 12, 4 to the vector AB, that should match what's in the circle, 4a plus 6b, 12a plus 4b, right? So just to repeat, this was the vector matrix A we started out with. Let's call that transformation T1. And this is the second transformation, T2. And the combined transformation, let's just call that T, is given by the matrix product of T2 and T1. And then the effect of applying C on the vector AB is the same as applying the two transformations one after the other, because this was the first transformation, this is the second transformation, we got this, so it works out to be the same. And in general, you can prove it for any transformation of anything. It's just a very simple exercise to show that, and it just follows from the definition of matrix multiplication. Okay? So any questions about that? Okay, you're really late, but you can go get that seat over there, and don't do it again. Okay. I mean, this is ridiculous. This is 15 minutes late. Okay. Any questions? So the main point is to understand that first, matrix is transformation, and second, transformation can be composed. Okay, so we can actually think about these transformations like this, and say that T1 composed with, which is some composition is going to give you a transformation. Yes.
So in one lecture you mentioned matrix multiplication is not commutative.
Commutative, correct.
So for example, if they do have like same dimension, they are commutative?
They're not, no, they still won't be commutative. So T1 times T2 in general won't be the same as T2 times T1, okay, even if they have the same dimension.
Suppose they are both square matrices and they are both transformation.
If they're both square, no, because again, it's, even if you think of it from the perspective of transformations, it's not necessarily the case that the transformations are going to commute, okay. You can actually just write out the terms, and you'll find that they don't have to be the same. Okay. There are some conditions under which they'll be the same probably, but I think if they're both diagonal, they probably commute, but I'm not sure of it. Okay. But in general, no. In general, transformations do not commute. So it is important that it's BA and not AB. Okay. If you do AB, you get something else. Okay. All right. So I want to now focus on a specific kind of transformation, and then we'll take a break. Okay. So I want to focus on this transformation over here. So this is the vector I'm going to look at, AB, and I'm going to focus on this very simple one, 2, 0, 0, 2, and which gives us the vector 2A, 2B. Okay. So what do we have here? We have some vector AB, and we're multiplying it with this, or pre-multiplying with this particular transformation A, or I'll call it T1 just to keep it as a transformation. And what's happening is that we can write the right-hand side where it looks like this, 2 times AB. Because if you remember, when you multiply a vector, a matrix by scalar, the scalar multiplies each element. So the scalar 2 multiplying AB is going to give us the matrix 2A, 2B. Okay, that's what's going on. So what we have here is this interesting phenomenon, which is that this one over here, which is a complicated operation, which is a matrix multiplication, can be replaced by a simple operation, which is a scalar multiplication. Okay, just think of it from a perspective of computer scientists. Okay, somebody's saying, I have this vector, let's say it has 1 million elements in it, and I have this matrix, which is 1 million times 1 million, right? It's a lot of work to compute. Each element is going to be 1 million products and 1 million adds. Okay, so, or 1 less than 1 million adds to be precise, 999,999 additions and 1 million multiplications, order of 1 million, right? But I can replace all of that with just 1 million multiplications, no additions, and the multiplication by the same scalar, which is much easier. Okay, so there's a dramatic simplification in the computation complexity, and so we kind of wonder, when can we do this? Under what circumstances does it become possible for us to take a transformation on a vector and replace it just by a scalar multiple? Okay, and the answer is that we can't do it all the time. We can't do it for everything. Okay, we can do it only for certain vectors. Okay? For a general matrix, you can only do it for certain vectors, and then for those vectors, these multiples over here turn out to be certain multiples. Okay, and so these are called the eigenvectors and eigenvalues. So this multiple over here is called the eigenvalue, and this vector for which it works is called the eigenvector. Now, in this particular case, we have a fairly straightforward transformation. We have a doubling transformation, okay, which is trivial. Okay, it's chosen to be trivial. So just by inspection, it becomes clear that this is going to work for essentially all vectors AB. Okay, so the set of eigenvectors for which it's going to work is basically all vectors. All vectors are going to be okay for this particular transformation. And the eigenvalue is going to be 2, because that's what it is, right? That's what you get over here. So we get this very simple thing. But what if I told you the matrix was not 2, 0, 0, 2, but it was 2, 0, 0, 3, right? Now what's going to happen is that we have this over here. You have 2A, 3B. So we can't put 2 over here. That's not going to work. It's not going to work. So what can we do? Okay, anybody have a suggestion? How do you get this to, how do you get an eigenvalue out of this? How do you get a scalar multiple out of this? Compute. No, I want to do it by inspection. I don't want to compute it. It's too much work. Yeah.
For example, there's a relationship between A and B.
What relationship between A and B will give it to you?
B is like 2/3 of A.
B is 2/3 of A. Yeah, that's one way of doing it. There's a very simple way of giving an eigenvector and an eigenvalue for this. Very simple. Yeah.
So if you multiply the matrix by the vector A0, it's just going to give you.
That's right. So let's say we zap this out. We make this a 0. Okay. Then this is going to become a 0 over here, because that's a 0 from there. And then we can say that this is basically 2A, 2 times A0. Remember, I'm not saying it's going to be true for all vectors. It was the case that when it was 2, 3, or 2, 2, it was for all vectors. But for this matrix, I don't have that. I'm going to choose a particular vector, the eigenvector A0, or for that matter, yeah, which is going to be anything that has a 0 here, actually, which means it will be 1, 0 in general, but A0. Then, no matter what I have here, I'm going to get the 2A0 over here. And then I'm going to get over here this one over here. So this, as you can see, this works. So the multiplication of this matrix on this particular vector A0 is going to give me a scalar multiple of 2, 0. Okay? And the other multiple just is going to be 0B, which is going to give me the value 3 times 0B. So it's very important to realize that the eigenvalue, this multiple over here, is not general. It's only for a particular eigenvector. So these things go hand in hand. If I tell you the eigenvalue, I'm going to tell you the eigenvectors that go with it. Okay? And the eigenvectors can be infinite, right? Because 0B is an infinite set, an infinite family of eigenvectors, but I'm going to have these hand in hand. So I can't just say here are the eigenvalues, here are the eigenvectors. They're not separate. You've got to compute one, and the eigenvectors go with it. Okay? And that's why I wanted to show you this over here, because you can see right away that with this matrix, you don't have this nice property that all vectors, no, it's got to be just this. It's also an infinite family, but it's going to be like, okay. So let's do the homework problem for the eigenvalues, because the easiest way to understand eigenvalues is to work with that example over here. So I talked about how to compute the eigenvalues for a very simple transformation, which was the scaling transformation of by 2, which was 2, 0, 0, 2, and then the other one. Okay. So let's look at the transformation for this matrix. Compute the eigenvalues for this matrix 1, 9, 4, 1, which was the homework problem. And the way to compute it is to essentially solve it, right? So if we do it like this, we know that. So let me first define what the eigenvalue is. Maybe I should do that. So we have matrix A. That's our matrix. And that's viewed as a transformation. And it's a square matrix, n by n. It's a square matrix. Okay. And we're going to apply it to a vector x. And that's a vector, which is n vector. Okay? And what we're saying is that the product of the matrix on the vector, or the transformation of the this transform for some x is equal to a scalar multiple lambda x. Lambda is a scalar. And this one is the same vector again. It's a vector. It's an n vector. Okay? So what we're saying is this complicated operation of a matrix applying on a vector can be replaced by just a scalar multiple. That's what we saw earlier. And we'd say for those vectors x, we call x the eigenvector, and the lambda is the eigenvalue. That's the formal definition of eigenvalue and eigenvector. So eigen, I believe, means right. Is it correct in German? Is that right, proper, something like that? So that's the meaning. So how do you compute the eigenvalues and eigenvector, corresponding eigenvectors for this matrix over here? We'll just write it out. We know that for some x, this vector, let's just say the vector is x1, x2. So this A times x should be equal to lambda times x1, x2. This is by definition. Okay, that's the definition right there. So we can write this like this. We just expand this out. We get this equation x1 plus 9x2 equals lambda x1, and 4x1 plus x2 equals lambda x2. This is just by expanding the matrix. And we should take lambda to the other side. We get this equation just over here. I'll just write this down. 1 minus lambda x1 plus 9x2 equals 0, and 4x1 plus 1 minus lambda x2 equals 0. Okay? So that's just, again, simple math. And so now what I can do is I can write this in a matrix form again. And the way I do it is to just simply write this in the form like this. I just say, here's a matrix, 1 minus lambda, and you get 1 minus lambda again, and 9, 4, okay, times x1, x2 equals the 0 vector, 0, 0. And again, just to keep things, I call this A, this x equals 0, okay? I haven't done anything complicated here. All I've done is to simply expand out the definition of eigenvector, eigenvalue, eigenvector to come up with this system of equations. And we recognize that the right-hand side is 0, so we call this a homogeneous system of equations. That's just the name for it. Let's see if we can apply Kramers rule to it. So let me just go back and remind you what Kramers rule is. Kramers rule says that xi, the ith value, okay, corresponding to this this one over here, this ith value of the eigenvector is given by d sub I over d, where d is the determinant of the matrix A, okay, and d sub I is the matrix A, is the determinant of matrix A, and the ith column replaced by B, by the right-hand side B. That's the determinant. Okay, that's the definition of Kramers rule. Now, the interesting part here is that B over here is 0. Since B is 0, the ith column is being replaced by 0. If the ith part is being replaced by 0, we can always expand by the ith column, right? And which means that you're going to get a determinant value of 0. So if you remember the determinant lecture, what we do is the value of the determinant is the aij value multiplied by the cofactor. It doesn't matter what the cofactor is. The aij value is going to be 0 for that column. And so all of the di's are going to be 0. So this is all going to be 0. What about the determinant of the matrix itself? Well, we don't know, right? But we know that all the xi's are going to be 0 for sure, right? Unless, there's an unless over here. It'll be 0 for sure because all the di's are 0, unless d itself has a value of 0. If it is 0, then the x sub I are going to be 0 over 0, which is unknown. 0 over 0 is undefined, right? So we have the following situation. Either the determinant D has a value which is non-zero, in which case all the xi's are definitely going to be 0, right? And so we have this trivial solution that a times x is lambda x, where lambda is 0 and x is 0, right? So we haven't got any information out of it. It's kind of uninteresting. You're saying ax is lambda x, yeah, sure. The eigenvector is 0, the eigenvalue is 0, and it's a trivial solution. You know, we didn't learn anything from it. It was no fun, right? On the other hand, if D is equal to 0, then x sub I from Kramers rule is 0 over 0. Then we don't know, right? Maybe x sub I has got some interesting values. You know, let's go find out, right? So the important thing here is that for this to work, for this to happen, we need to have the matrix, this matrix over here, A, to have a 0 determinant, okay, which is what's going to make our life interesting, okay? So this step is critical, okay? So I want to make sure everybody understands that. So are there any questions about this so far? Okay. So I'm just applying straightforward application of the principle that if you have a linear system of equations, which is what we did last time, Ax equals b, then Kramers rule tells us that x sub I is given by di by d, and the d sub I by definition is the matrix, the determinant of the matrix A, where the ith column is replaced by b. It's homogeneous, so b is 0, so d sub I is also all 0, so x sub i's are all 0, right? Unless the determinant d is also 0. Okay, that's the chain of logic, and it's a, you know, obvious and straightforward chain of logic. You can't get around it. Okay, but the consequences are huge. Okay, which is why I'm kind of pushing this point here. So are there any questions about this? So what we're going to do here now is to look at the system. I'm just going to erase this for now to give me some space, and say that this matrix has a determinant of 0. So I'll take this and replace this with this vertical value here, and say this determinant is equal to 0. That's what I said, right? Again, why is this 0? So that we have interesting values of the eigenvector x sub s. Okay, so what does this give us? We can expand this. Okay, if you remember, for a determinant of the thing a, b, c, d, it was equal to ad minus bc. That was the definition of a 2x2 determinant. So if you do this, we're going to end up with this determinant, basically 1 minus lambda square minus 36 is the determinant, okay? And this is equal to 0, because we said that determinant A equals 0. This implies 1 minus lambda square minus 36 equals 0. And I chose these numbers, you know, carefully so that I don't have to do much work. And so we get 1 minus lambda square. 1 minus lambda square equals 36. So 1 minus lambda equals plus minus 6. And so lambda equals either 5, what is it? Okay, let me do this. Minus 5 or 7, okay? So there are two values of lambda that I got out of here, okay? So what does this mean? It means that there is some vector here. There's some vector here which we haven't figured out yet, but we will in a minute, such that when this matrix multiplies that vector, it's as if it were multiplying by the value minus 5, and there's some other vector here, so that if you multiply A by that, it's like multiplying by the value 7. Okay, it's kind of funny. I've told you what the multiples are, but I haven't told you what the vectors are. Okay, and that's just the way it works out. Okay, it works out that you find out the eigenvalues first before you find out the eigenvector, though it's logically speaking, we don't want to think about it that way. We want to say, here's a matrix, and if you multiply this vector, it's like multiplying by minus 5. And if you multiply the other vector, it's like multiplying by 7. But we don't do it that way. The computation actually works backwards. Okay, and that's confusing. At least I found it confusing. When I was studying eigenvalues and eigenvectors, I'd say, yeah, okay, great, I got the eigenvalues, fantastic. So I'm done, right? No, I'm not done, because all I've told you is that there is this unknown vector which is going to be scaled up as if it's a linear scaling by 5 or minus 5 or 7. Okay. Any questions about this so far? I mean, you've done all this hopefully in your homework, but I'm trying to give you the intuition over here. So now let's just focus on this one, lambda equals minus 5. And to find what that vector is, we'll go back and put it over here. So we don't need to actually go, we can go right here. So we have 1 minus lambda x1. So let's go just do that. Okay. So we get 1 minus, okay, so we want to do this, just 1, 9, 4, 1 times, by definition, x1, x2 equals minus 5, x1, x2, okay, which you can expand to get x1 plus 9x2 equals minus 5, x1. Okay. What did I do here? Okay, and right for the first row, and the second one is that 4x1 plus x2 equals minus 5x2. Okay. So what you'll find over here, whenever you do this kind of computation, is that you will find that you have what looks like two equations, but there's actually only one. Okay, it's always going to be the case that one of them is a linear combination, or is a scalar multiple of the other. Okay, it's always going to be the case. And the reason for this is because it's actually, can anybody explain why it's going to be that these equations? You only have one equation. Why is that? Okay, there's a specific reason why.
The determinant is 0.
The determinant is 0, correct. The rank is 1. So this is going to have a rank of 1. Okay, actually this matrix over here, actually specifically, this matrix is going to have a rank of 1. Okay, because this matrix is same as that. I just moved it over here. If it has a rank of 1, you can't have two linearly independent equations coming out of it. Okay, and the rank is 1 because we chose the matrix to have a determinant of 0. Right, we chose this value of lambda such that it was singular. It had a determinant of 0. So if the determinant is 0, if you remember, if the determinant is 0, the rank cannot be full rank. You cannot have an n by n matrix with a rank of n if the determinant is 0. Okay, so there's an if and only if thing. So if the determinant is 0, the rank must be less than n. If the rank is less than n, it must be the case that these are linear combinations. Now we only have two, so obviously we can't have two separate equations. If that were the case, then our computation is wrong. This can't be the eigenvalue. Okay, so always when you do eigenvalue type problems, when you go back to this and apply it over here, you'll find that at least one equation is going to be redundant. Okay, again by definition of, by choice of the eigenvalue. Okay, and if we solve this, we basically get it's underdetermined, and so we get x2 equals minus 2 or 3 x1. Okay, and so the vectors that correspond to this are basically of the form a times 1 minus 2 over 3. Okay, so that vector 1 minus 2 over 3 multiplied by any constant a is an eigenvector corresponding to the eigenvalue of minus 5. So if you want, you could kind of say this is the eigenvector, this is the eigenvalue of minus 5, and that's one solution to the homework. Okay, so again what you're saying is that this matrix, when applied to any vector of this infinite set of vectors of the form a times 1 minus 2 by 3, is going to give you the effect of a scalar multiplication by the value minus 5. Okay, and the similar set of reasoning is going to give you the other vector, which is going to say that it's a times 1, 2 over 3 is going to give you the value 7, and that's the other solution. Okay, so for those of you who are grading, so all of you should be grading somebody's, and that should be the answer over there. Okay, so 1, 2 over 3 times some constant and 1 minus 2 over 3. Okay. So any questions about this so far? Okay. So I'm going to now going to keep that up here, and I'm going to actually now write down the general form of the solution. This is a specific example to fix your ideas. Let's do the general case, and I'll give some terminology as I do that. So, okay. Oh, okay, let me actually show the geometric interpretation before I move on. So, what we have over here is that these vectors that I have over here are particularly simple. They can be drawn in two space. So the matrix is, if you recall, 1, 9, 4, 1. And that's some transformation. What we're saying is that if we have a vector in the direction 1 minus, okay, let's just do plus 1, 1 plus 2 over 3. So let's say this is 1, and so 2/3, so this is 1. Okay, and so 2/3 is about over here, so we have this vector over here. Okay, right. So let me actually do something a bit more interesting. Let's take this value 1, 1, this vector 1, 1, and what happens if I apply this matrix to the vector 1, 1? What I'll get is the vector 10 and 5. Okay, do you see that? So it's 9 plus 1, 4 plus 1 is what I'm going to get as the vector 10, 5. So if I take 1, 1, and let's say this is 10 over here, and this is 5 over here. So 10, 5 is somewhere over there. So 1, 1 is like this, and that becomes that one over there, 10, 5. The important thing is that there is this kind of angle over here. It's this transformation is scaling up and also rotating a little bit. Okay, so you get the scale and rotate at the same time. Okay. However, when you apply this to the vector 1, 2/3, okay, which is the eigenvector over here, what happens is that this 1, 2/3 is going to go to 7 times that, which is going to be 7 and 14 over 3. And so 7 is somewhere over here. And I don't really, and I'm going to 14 over 3, I'm just going to tell you where it is. It's going to be somewhere over here. Okay, so this is going to be 14 over 3, which is whatever, 4 and somethings. Okay. This is not a linear scale, but the important point is that this particular eigenvector is going in the same direction. It's just the linear scaling, because scaling of a vector means go in the same direction. Okay, that's what we do. When you double a vector, x, vector x goes to vector 2x, you're going in the same direction, you're just doubling it, right? So here we are multiplying by a factor of 7 into 7. Okay, maybe we should make it star. So this particular matrix, this transformation is operating on this special vector 1, 2/3 vector in such a way that it's scaling it by a factor of 7. Okay, and similarly, it's acting on a different 1 minus 2/3, okay, which is going to be somewhere x is x is 1 and minus 2/3, so somewhere over here. That is also going to be times 7. But every other vector not on that line is going to get rotated in some way, either towards or away from the axis. There's always be this angle theta, which is going to be 0 only for this thing. So we can view this matrix transformation as a linear scaling going in the same direction only for these guys. Okay, we have another sleeper here. So Kellen, can you wake him up? Okay, thanks. You're awake? Okay, thank you. Any questions about this? Okay. All right. So let's look at the general case, and then some terminology that goes with it. So in the general case, what we have is we have the equation AX equals lambda x, where A is a matrix, X is the same thing. And so we simply move lambda to the other side. So we get A minus lambda I times X equals 0. So that's just moving lambda x to the left-hand side. And because lambda is a scalar, we need to multiply by the identity matrix I to get this over here. And we say that this is a homogeneous set. This is a homogeneous system of equations. So it has non-trivial solutions if and only if the determinant A minus lambda I is equal to 0. Okay? And now we know why we had to study determinants last lecture. Because all this stuff makes sense only when you study determinants. So determinants are boring, but from the determinants we get Kramers rule. From Kramers rule we get eigenvalues. So we need to kind of make that step. So this summarizes the example and logic quite straightforward. And so this equation is very, very important. Okay, it's a very important equation. A minus lambda I determinant equals 0. And this is given a specific name. It's called the characteristic equation. Okay, it's called the characteristic equation of the matrix A minus lambda I equals 0. Now, this equation, if you look at it, is going to look something like this. It's going to have some, let's call it, so it will be some A11 minus lambda, okay, and then some other elements over here. It's going to be, and this will be all constants, A22 minus lambda, and then some other stuff over here, and so on. And the last element is going to be ANN minus lambda. Okay, that's what this determinant is going to look like. Okay, and we see that it's basically going to be a polynomial in lambda. Okay, it's going to be a polynomial in lambda. And what's the highest degree we can get out of it? Well, at most we're going to have lambda multiplied by itself n times. We're going to have lambda to the n. That's the highest degree of lambda we're going to get. It's a polynomial in n. Okay, where lambda is the unknown. Okay, and so we call this, okay, sorry, that's the characteristic determinant. Okay, sorry, I take it back. That's the characteristic determinant. This polynomial in lambda to the n is called the characteristic equation. Okay, that's the characteristic equation of the of this matrix. And this basically, when you solve it, like we did earlier, gives us those values of lambda for which are the eigenvalues of the matrix. Okay, the eigenvalues, and then corresponding to each eigenvalue, there will be an infinite set, typically an infinite set of eigenvectors. Okay, so we know from the what's called the fundamental theorem of algebra that any polynomial which has of degree n is going to have up to n roots. Okay, up to n roots, because we're trying to find this. So we have some polynomial in n. So this is polynomial in lambda to the n equals 0. That's the characteristic equation. We're going to set this thing equals 0, right? So we're going to have some polynomial equals 0. This is just a polynomial in n, and we know from the fundamental theorem that it has n less. Okay, it has less than or equal to n distinct roots in C, in the complex plane. So we're going to have possibly complex values, but that's comes directly. So what this means? It means any matrix, any square matrix, will have up to n eigenvalues. Okay, where this can be complex. Okay, so we get that just from simple kind of algebra and just from looking at the structure. And that's a pretty powerful statement to make, because we're not saying that, oh, some eigenvalues may exist, because I'm taking a transformation. Any transformation, it's not that only for certain vectors, because I have this magical thing, it's a scaling. Okay, and you can say, yeah, okay, I can do it for 1, can do it for 2. No, if it's of size n, there'll be n scalings, okay, up to n scalings, and at least one exists, right? And it's going to be complex scaling. Again, let's not worry about complex for just a moment, but we know these eigenvalues exist just from the fundamental theorem of algebra. Okay, up to n of them exist. So it's this very nice existence proof. Just because n roots exist, we know that n eigenvalues also exist. Up to n eigenvalues also exist. Okay, so that's a nice thing that comes. Okay, and each eigenvalue will be corresponding to a family of eigenvectors. It will be not one eigenvector, but a family of eigenvectors. Why? Because the rank of this matrix is going to be less than n, which means that we can't fully solve it, so we'll always have a family, an infinite set of eigenvectors along a particular dimension, characterized by this one value. And so we can sort of think about families of eigenvectors, an infinite set of eigenvectors corresponding to each eigenvalue. Now, when you go beyond 3 dimensions, it gets very funny. Let's say a 25 dimensions matrix, 25 by 25 matrix, and you say, yes, there is a scaling in 25 dimensional space. It sounds really exotic. All that means is that multiplying by this 25 dimensional matrix is exactly like taking a scalar and multiplying a 25 dimensional vector by that value. Okay, but the physical representation of this is impossible. I mean, what does it mean to have 25 dimensional space? It doesn't matter. Okay, we just kind of find out what's the scaling over here, and the scaling exists, and we'll have up to 25 different scalings depending on the kind of equation. Okay, any questions about this over here? So just to show you some complex eigenvalues, let me do one more example with just a trivial eigenvalue. With let's just take the transformation 0, 1, minus 1, 0. And so if this is A, then what you're going to get that the characteristic, you can write down the characteristic determinant by inspection as minus lambda 1, minus 1, minus lambda, right? This is just, you can just write it down without even going through all the intermediate steps, because A minus lambda I determinant is this. And this one is basically saying lambda square equals minus 1 is going to be the characteristic equation, because you get lambda square plus 1 equals 0. And so lambda equals plus minus I. So it's just a complex I. And so the set of values of the eigenvalues is given a name. So I'll just write it down. The spectrum is basically the set of the lambda I. Okay, and the largest or eigenvalue by magnitude is called the principal eigenvalue, or dominant if you have more than one. So the magnitude of this is 1, because it's I is magnitude 1. So the dominant eigenvalues in this case are plus minus I. Okay, so we don't have principal, but we have dominant. Okay, it's just a, and it's also called, and the largest magnitude eigenvalue is also given the name spectral radius. Now, why do we give it these names? Okay, and the reason is because of the following. So if we draw the complex plane where we have the real axis over here and the imaginary axis over here, all these eigenvalues are going to be somewhere on the complex plane. So for example, plus minus I means that we have eigenvalues over here, okay? And we could have other eigenvalues as well. So it looks like a bunch of stars in the sky, okay? For mathematicians who spent all their time in, MC and haven't really gone outside, they think it's stars in the sky. So it's a spectrum, of stars. They're kind of impressed by it. And the magnitude is going to be the distance, the radial distance, okay, because the magnitude of a complex number, a plus bj, or a plus, we'll use j instead of I in this course, it will be square root of a square plus b square. And that's just the radius. That just tells you the Euclidean distance from the point to the origin. And so this clearly is the radius. The largest magnitude is going to be the radius of that circle, okay, in the complex plane. And we're going to see the, so this is the principal eigenvalue right there. And so we know that all the eigenvalues lie inside the circle, so that's what's called the spectral radius, okay. Now for those of you who are not familiar with complex, I don't know how many of you, okay, all of you have seen complex numbers before, but most of you may be not quite familiar with the complex numbers. When I start doing signal system transforms, I'll do a revision on complex numbers so you will be back up to speed on it, but this will become much more clearer hopefully at that point over here. I'm just going to finish this up just to tell you what the eigenvectors are, and then we'll take a break. So we just say, to find the eigenvectors, we say 0, 1, 1, 0, sorry, minus 1, 0, x1, x2 is equal to I, x1, x2 to find the corresponding eigenvector, and we get x2 equals I, x1 minus x1 equals by x2 just by expanding this out. And so one satisfying thing would be a times 1i. Okay. And so this eigenvector corresponds to, I'll just write this over here, this is the eigenvector to the value I. And similarly, you can find another eigenvector pair, which is a times 1 minus I, and this corresponds to minus I. The geometric interpretation of this is quite easy and quite fun. What it's really saying is that the eigenvalue of this, so this is actually a rotation matrix. Okay, for those of you who've seen rotation matrices, you normally have cos theta, minus sine theta, cos theta, or whatever. I can't remember the exact thing over here. I've chosen this to be actually, I think, pi by 2. Yeah, it's a pi by 2 rotation. And what this is saying is that the matrix is rotating, okay, by 90 degrees. Okay, so if you give it an angle, it's going to rotate at 90 degrees. What this is saying is that if your initial value is complex, 1i, then the rotation leaves it unchanged, okay, which is kind of funny. Okay, so you're saying any real value, any real vector is going to be rotated 90 degrees, but a complex vector, which is 1i, is unchanged. Okay, now what does it mean to a complex vector? I don't know. I spent a lot of time thinking about it, and I couldn't figure it out. So I just wrote in my book, it says, rotation matrix, because when you think about it, you say, yeah, rotation matrix, which is this, is going to rotate all things, right? So over here, I showed you rotation. This matrix is rotating the vector by theta degrees. So I chose this to be a rotation matrix like this to see, okay, what happens? Because I'm supposed to rotate everything. And the answer is, yes, I'm going to rotate everything that's real. Okay, but everything that's complex, it won't rotate. So we have sort of a fixed point in complex space, and okay, I don't know what it means. If you can figure it out, let me know, but I don't know what it means. Let's do some simple, fun eigenvalues because it's easy. So here's the eigenvalues of a diagonal matrix, because this is easy and fun. And it turns out to be important later on. So let's consider a diagonal matrix of the form A11, and these are all zeros here, A22, ANN. What are its eigenvalues? Okay, so we can actually compute it pretty straightforward by using the first principles. You have x1, xn equals whatever, lambda x1, xn. So using the same trick as before, we find that the characteristic polynomial is going to be a11 minus lambda, a22 minus lambda, ann minus lambda. This determinant equals 0 is going to be the characteristic determinant, and the polynomial is going to come from it as a characteristic polynomial. Okay. How do we expand this? Okay, let's just see what it's going to be. It's actually, by inspection we can see it. So we take, we expand by this column over here. So we're going to take this one, a11 minus lambda, and multiply it by its cofactor. So it's a11 minus lambda multiplied by the cofactor. Okay. First of all, notice that all the other values are zeros over here, so we don't really have any contribution from there. All we're going to get is a11 multiplied by the cofactor. Its cofactor in turn is going to be a22 multiplied by its cofactor, right? And that's going to be a and n multiplied by its cofactor all the way down, right? And all you're going to get basically, and these are all going to have I plus j values, which are plus. Okay, because you're going to have I plus this 2, 2, 3, 3, whatever it's k, so it's always going to be 2k, right? So minus 1 to the I plus j is going to be always 1, so we can ignore that value. And all we get is this a22 minus lambda, ann minus lambda. That's the determinant right there. Okay. And any questions? So if you remember the determinant, basically this is what you get. You can just actually do it if you want at home and try it out, and you'll find that you get this as the equation. And this is a nice equation in lambda. It's a polynomial in lambda, which is already factored for us. Okay, it's already factored for us, and so we know that the equations are lambda equals a11, lambda equals a22, all the way up to lambda equals a and n are the n solutions to this equation. So the polynomial in n which has n solutions, and these are the n solutions right there. You can just read them off. It's as simple as it gets, already factored for you. And what does this mean? It means the eigenvalues are exactly these. These are the eigenvalues right here. All the way up here. I can look at a diagonal matrix and say, yeah, these are the eigenvalues. I got it. Okay. Right, so when I started out with the vector 2, 0, 0, 2, what are the eigenvalues? 2 and 2. We have 2, 0, 0, 3, what are the eigenvalues? 2 and 3. Remember, each one has its own different eigenvector. In fact, the eigenvectors are also easy. The eigenvectors corresponding to the ith one is just going to be 0 and xk and 0. That's the kth eigenvector. Okay, because we're going to have this. And so if you want to make it, you can just say a times 0, 0, 1 over here. That's the direction. It's going to be basically a bunch of what I call orthonormal, mutually perpendicular vectors, which have the 1 in the kth row. Okay, and that's right there. You have the eigenvalues and the eigenvectors just by inspection. So diagonal matrices are fun. You just look at them and you say, here are the eigenvalues, and here are the eigenvectors. So you can just write it down without any work. Okay. So any questions about that? Yeah.
What if two of those are the same number?
Right. Then we just get a repeated. We get the repeated eigenvalues, right? So you have up to n distinct values. Okay. So in this case, if you have, let's say, 2 of them or 3 of them are the same, then we're going to have fewer numbers to work with over here. So we get a repeated eigenvalue. Okay. When you get a repeated eigenvalue, from the perspective of eigenvalue computations, that's not a big deal because you just have fewer. You have up to n solutions. We don't have to have n solutions. Imagine x minus lambda to the n, it only has one solution, right? Or sorry, lambda to minus a to the n, it only has one solution, lambda equals a. So we have up to n. When we talk about stability of control systems, repeated values of roots will have a meaning. But we won't do that now. When we talk about control theory, we'll talk about that. But for the purpose of, from a mathematical perspective, it's not a big deal. Okay, just a repeated root. And these could be complex as well, right? I mean, there's nothing that says that these have to be real. We could have matrix with complex values as well. Okay. Typically, in real physical systems, these are going to be real matrices, real values. We won't have complex values. But again, there's no reason why these can't be complex. Any other questions over there? Okay, so I'm going to talk briefly about why are eigenvalues important, and then I'll try to do an example, otherwise we'll continue with the example next time. So let me do a geometric example here, and then I'll do the actual numerical stuff next time, because I think that would actually be better. Okay, so let's just take a two-dimensional space of vectors, and let's say that the eigenvectors point like this, okay? The eigenvectors point like this in this direction and that direction. Let's assume that the eigenvectors are real, okay? So we have x1 along this axis, x2 along this axis, and we saw earlier what this means. You know, earlier we had the eigenvectors of 1 2 by 3 and 1 minus 2 by 3. It doesn't really matter, okay? So let's say I have some other point over here, another vector. So let's call this eigenvector 1. So I'll call this E1, and this eigenvector 2 is E2, and I have some vector V over here, okay? Now I can always decompose it into these eigenvectors, okay? Right. And one result that is useful is that it can be shown that the vectors, the eigenvectors form a basis of the space. Okay, the eigenvectors will span a space called the eigenspace. So the eigenvectors form the basis set of the eigenspace. In other words, we can the eigenvectors are going to be independent of each other. Okay, it's easy to show that eigenvectors are independent, linearly independent of each other, and we can find the set of vectors which can be expressed as linear combinations of the eigenvectors. Okay, if you can find the set of it's an infinite set of vectors that are linear combinations of the eigenvectors, we call that the eigenspace. That is the space of vectors spanned by the eigenvectors. Now, here I have two eigenvectors, and when I say they're linearly independent, all that means is that we don't have them on the same direction. They're going to be in different directions. As long as in different directions, even slightly different directions, okay, they span the space, right? Because you can always add and subtract them to get, you know, any other vector that we want. So these two vectors over here can be composed to form essentially any other vector v, and the eigenspace over here is going to be the real plane. It's going to be the entire real plane. Any vector v can be expressed as the combination of this. Now, when we go and apply the matrix to this eigenvector, it's going to scale it up like this, and we apply it to this one, it's going to scale that up like this. And so when we apply it to some vector v in this eigenspace, it turns out that the effect of that is essentially to take these two combinations and do the linear combination of them to give the same thing over here. So in other words, to compute the effect of the transformation on an arbitrary vector v, all I need to do is to decompose the vector v into a linear combination of the underlying eigenvectors that form the eigenspace, and then I can just apply the transformation. So if I want to apply the transformation repeatedly, I know that each application is going to just scale it up linearly, okay? And that's going to scale this up linearly, so I can just take these two linear things, combine them together, and then I'll get the effect of this transformation on this vector v. We'll do the sort of numerical thing, you know, in the next class, but I just want to give you the idea here. So this is a very powerful result, okay, because I'm now telling you, you can take any matrix and any vector, okay, and essentially figure out how to compute the effect of that matrix on that vector without doing much work. All you need to do is multiply the vector with the corresponding scalings, the eigenvalues, when we decompose it into the appropriate linear combination of the eigenvectors. So these eigenvectors now become very important. Okay, they become the basis for the space, and so I just need to take my vector that which is not an eigenvector, and then figure out how it maps onto these eigenvectors, and then I can figure out the effect of the transformation. Okay? And in many, many cases, what we really care about is not one transformation, but repeated transformation. You want to apply it once, apply it again, and see what happens. And to do that, it turns out that all we need to do is take the vector, decompose it, apply it to all these, which is just a scaling. At that point, we can just reconstitute the original, the effect on that vector over here. Okay, and we'll study that sort of numerically in the next class. But are there any questions about that here? Okay, so just one last thing, because we have a minute. Does some of you replied to that poll in the homework questions? So if you can take a minute and respond to that, that will help me to determine how effective the homework questions are. Okay, and could you please drop that off over here? Thank you.